So, 8085 pins, so if we look in terms of some grouping of them, that is the related pins, we keep them together. So, the pins which are doing a particular function. So, if you see this, the first group of pins that we will find corresponding to the address bus, and as I said that my address bus in case of 8085. So, this is 16 bit. So, they are named so this is A0, A1, A7, A8, A9 up to A15. So, out of that this A0 to A7, see this is lower order address bus consisting of lower order 8 bits, and A8 to A15. So, this is the higher order address bus or higher order address bit. So, we should better if I write this most significant bit in on the left side. So, I should write it like this. Okay. So, A7, A6 up to A0. So, this is the higher order bus, higher order address bits, this is the lower order address bits. So, this higher order address bits, so they are coming from the higher order address bus. So, pin number 21 to 28, they form this higher order address bus, and they are this A15 to A8. So, A15 is pin number 28 and A8 is pin number 21. Now, this lower order address bus, so A7 to A0, so that is multiplexed with the data bus. So, this this is allocated pin number 19 to 12. Okay. So, these 8 bits, so they are giving me address sometimes, and also sometimes it will act as the data bus. So, these pins 12 to 19, sometimes it will act as lower order address bus, sometimes it will act as the data bus. Now, the address bus is going out from the processor to the memory, and the data bus may be bidirectional. So, as a result, this higher order address bus is going out of the memory, and this lower order address bus which is multiplexed with the data bus. So, this is bidirectional. Okay. So, apart from that, we have got some other important pins like this ALE signal. So, this ALE signal will be used to tell the content of this multiplexed address data bus. So, when this ALE signal is high, then the processor has got the address put onto this multiplexed bus, and when the ALE signal is low, then this bus may be used as the data bus. So, when the address is put, this ALE signal is active. So, when address is not there, ALE is deactive. So, it may in that time this data this is treated as a data bus. S0, S1 IOM bar, I have already said that they are giving me the status of what the processor is doing now. Then read bar and write bar, so they are actually telling what operation the processor is doing, is it a memory read operation or a memory write operation. And IOM bar, so this is actually the pin that tells the operation that the processor is doing, is it accessing a memory location or it is accessing some IO device. So, if it is accessing an IO device, so in that case this IOM bar line will be equal to 1, and if it is accessing a memory location, then the IOM bar line will be equal to 0. So, if IOM bar is 0 and this read bar is also 0, that means the overall the processor is doing a memory read operation. Similarly, if IOM bar is equal to 1 and this write bar is equal to 0, that means processor is doing some IO write operation. So, it is doing a write operation on some output device, it is accessing some output device. So, this way this IOM bar, read bar, write bar and S0, S1 etc. So, the S0, S1 we will see later. So, that gives us some indication about what the processor is doing at present. Then we have got some additional pins like SID, SOD lines I have already said. So, they are for serial input data and serial output data. So, if you so this 8085, so it has got the feature by which it can get data from outside world serially through the SID pin, and it can also output some data to the outside world by the SOD pin. So, that is serially the data will go. There are some ways by which you can interrupt the operation of this processor. So, that is by means of these lines trap, RST 7.5, 6.5, 5.5 and INTR. So, we will look into these interrupt issues later, but they are actually to tell the processor to suspend the current operation whatever it is doing and do some special operation for the system. So, it may be that something special has happened, like user has pressed some key, So, that has to be acknowledged, so that value has to be read and all, or maybe there is some emergency situation has occurred, some fire alarm has gone up. So, that way that has to be detected and that has to be taken, some special action has to be taken. So, these are the interrupts that are coming. Then you can, whatever the processor is doing, so you can give it a reset signal by pin number 36. So, activating this pin number 36 will reset the 8085 processor, and so whatever operation it was doing, it will abort that operation, the whole system will be reset. And when this reset in is activated, so this 8085 apart from resetting its internal registers and all, so it will also send output the high on the reset out line. So, if my system consists of the 8085 processor and number of other devices, so those devices can also be reset by this reset out pin. Now, for getting the clock to the system, so we have to connect some crystal between pins 1 and 2. So, crystal is connected. So, accordingly the 8085 generates the clock, and through this pin number 37 this clock is also outputted. So, if you want to use this clock to some other circuitry, so you can do that in using this pin number 37. So, most of the lines we have covered. Another important line that we have is hold and hold acknowledge. So, hold is actually telling the processor that that there is some other processor in the system. Like what happens is that if you connect say 2 such 8085 chips in a system and they are accessing the same memory. Okay. So, at some time this address and data bus will be driven by first 8085 chip, sometimes it will be done by the second 8085 chip. So, if there is no coordination between the two, then they will be accessing, try to access simultaneously, and the data corruption will occur. So, what is done is that we have this hold pin. So, if whenever one processor wants to access the bus, so it will say, it will give a hold to the other processor, and as a result this other processor will generate a hold acknowledge, and after getting the hold acknowledge only, the first processor will understand that okay, the other processor has released this address bus and data bus for my usage, and then it will proceed to use those address data bus lines. So, this way we can have multiple bus masters connected in a system, and they will be controlled by this hold and hold acknowledge lines. Okay. So, coming to the system bus. So, this system bus, so these are the wires connecting memory and I/O to the processor. So, you remember the diagram that we have shown previously. So, this is your CPU. So, we have got this memory and I/O. So, this is my system bus. So, CPU, this memory and this I/O, they all hang from the system bus. So, the wires connecting memory and I/O to the microprocessor. So, this is our system bus. The system bus, so though I have shown it as a single bus, so in reality it consists of 3 different buses: address bus, data bus and control bus. So, again if I look into this memory and CPU connection in more detail. So, this is my 8085 processor and this is the memory. Now, the address lines, so they will go from 8085 to the memory chip. So, these are the address lines. So, address line is going to be unidirectional. So, this will also go to some I/O devices. These address lines also go to the I/O devices to tell which I/O devices are which I/O device it wants to access. So, if it 8085 wants to access memory, so it will be giving address for memory location. If it wants to access some I/O device, it will give the address to the I/O device. Now, address bus is unidirectional, it goes out of 8085 and goes to the I/O device or memory, and it is used to identify the memory location or the I/O device location. Now, there is data bus. So, data bus is a bidirectional, because I can have transfer from 8085 to memory or from memory to 8085. So, read and write both operations are possible. So, this is going to be a bidirectional one. So, it is also connected to the I/O devices. So, this is bidirectional connection. So, this is data bus is bidirectional and for transferring data, and we have got this control bus consisting of other signal, control signals, synchronization signals like that. For example, in case of 8085, so we have got a number of signals like say the read bar line, the write bar line. Okay. So, all these lines that we have, so they are connected like this. So, there may be more such synchronization lines. So, as we look into more detail of this design, so we will see. So, this this part is known as the control bus. So, this is called control bus. So, this the first upper one is the address bus and this one is the data bus. So, we have got address bus, data bus and control bus, which constitutes the system bus. Okay. So, let us look something inside somewhat inside the 8085 microprocessor. How does it look like? So, this 8085 microprocessor, if you look into, so first you will find a number of registers. Okay. So, there is a special register called accumulator. So, which is as the name suggests, it accumulates the value. So, whenever you are doing some arithmetic or logic operation in the processor, then one of the operands of that operation must be the A register and the result is also stored in the A register. So, if suppose I am doing an addition operation, then this addition operation one of the operand must be in the A register and the other operand may be in some other register or it may be some memory location, but the result will again be stored in the A register. So, the advantage that it gives is that if I am doing some addition operation, then you see that there are three things to be mentioned: the source 1, source 2 and destination. Fine. So, source 1 and source 2 are two registers or memory locations, and ultimately the operation to be done is this D gets the value of S1 plus S2. Now, if we do this, then I need to specify three different operands S1, S2 and D. So, in case of 8085, the designers they have said that S1 must be A and this destination must be A. Okay. So, these two are fixed. So, these two are accumulated. So, the instruction simplifies to add S2. So, it may be for example, say add B. So, that will add the B register content with the accumulator to get the value. Now, here you see that we have got this accumulator register. So, this is a special register. So, its output goes to the arithmetic logic unit and there is a temporary register. So, where it holds the other operand for this arithmetic logic operation. So, whenever we are doing say add B, so what happens is that this temporary register gets the content of B register and after that it is the operation is done by this arithmetic logic unit. So, this arithmetic logic unit as we know that is a purely combinational unit, combinational circuit. So, if its inputs are fluctuating, then the result will also fluctuate. So, if it is coming from some register, then definitely the inputs will not fluctuate. So, whenever it is giving, it is told that you do the operation of addition. So, it will this arithmetic logic unit will do that. So, this is the temporary register. Then there is a set of flip flop or called flag flip flops. So, they are actually telling the status of the last operation that last arithmetic logic operation that has been done. So, it may so happen that after doing the operation, so there was an overflow generated. So, there is a particular bit in the flag register which will be set, or it may so happen that the result becomes 0. Okay. So, in that case again some flag bit flag flip flop is there which will be set and it will tell you like what is the content of what was the status of the last operation. So, that way it is used. Okay. So, these are the special registers, plus there is a set of general registers like this B, C, D, E, H and L. So, these are 8 registers that 6 registers that we have. So, all these registers are 8-bit registers. So, they can be used as operands for this arithmetic logic operations. As I said that add B. So, when I say add B, I am actually referring to this B register. Okay. So, that way I can have add C, add E like that. Okay. So, they are these are the B, C, D, E and H, L. So, these are some registers. Now, there are some special registers like there is something called an instruction register. So, this instruction register, so this is actually holding the instruction obtained from the memory. So, as I said that every time, so when this 8085 starts, so in the first instance, so it gets the first instruction from the memory. So, after getting the first instruction, so it needs to decode it. So, before decoding, the instruction is when it is fetched from the outside world, so it is loaded into this instruction register. So, in the successive phase, this instruction register content, it goes to this decoder where it performs this instruction decoding, and this instruction decoder output. So, that actually identifies the instruction that it is going to do, and then it is given to this timing and control module. So, which will generate all the control signals that will be needed at various time instants to do the operation. So, we will see some timing diagrams later which will tell you like how these control signals are to be generated, and then so this timing and control unit. So, this generates different control signal based upon this clock circuitry that we have. So, these clock signals that we are getting. Now, apart from that, there are some special registers, like there is a program counter. So, this program counter, it holds the memory address from where the next instruction will be executed. So, as I said that when you reset the processor, then this 8085 comes to a special address, and in case of this 8085, this address happens to be 0, the address location 0. So, if you reset the processor, then this program counter gets the value 0, so that it will be accessing the next instruction from location 0. Now, as the first instruction is fetched, this program counter value is automatically incremented and it points to the next instruction to be fetched. So, when the processor goes to the next fetch cycle, again the program counter output is put onto this address bus. This is higher order address bus and this is lower order address bus. So, this program counter content comes to this address bus, and then it is the instruction is fetched from the memory, and that comes again to the instruction register, that goes into this decoding, and that decoder will be generating will giving information to this timing and control, that will give controls for the execution. So, after this is over, again this program counter output is put onto this address buffer and address data buffer. So, that way it will go. So, this program counter is a special register which tells like what is the next instruction, the address of what is the address of the next instruction to be executed. Now, for this program counter, so we have got incremental and decremental address latch. So, sometimes so automatically the address register content, the program counter content has to be incremented or decremented. So, that is done by this one, this address latch. So, it is doing the increment decrement, and there is a stack pointer. So, we will come to its usage later. That is, there are some special operations that are needed to be done in the in any processor for storing the return address from subroutines, and the stack pointer is used for that purpose. So, we will come to that later. So, apart from that, so you will find a module which is known as the interrupt control. So, this interrupt control actually handles all these interrupt lines. Okay. So, accordingly it will tell the processor to suspend current operation, do something else, and that will be coming to this timing and control unit also to tell it like what to do. And there is a serial IO control input control line, SID and SOD. So, that module will be doing this serial communication. So, this is more or less the internal view of 8085 processor. So, as a user of the system, so we know that okay, there is a special register A, and there are some general purpose register B, C, D, E and HL. So, these are the 7 registers that we have in our repository. So, I can use these registers for writing programs for the processor. And apart from that, there are some flip flops which are the status flags, and from the manual of the processor. So, we will know what are the arithmetic logic operations that the processor can do, and accordingly we can that will tell you what is the functionality of the ALU. So, to summarize, this 8085 microprocessor, it consists of control unit, ALU, registers, interrupts and internal data bus. So, control unit, it will control the processor operation, ALU will perform data processing function, then these registers, they provide storage internal to the CPU. So, this registers if you have got some data, so normal way to have the data is that have it in the memory, from there fetch it. But normally in case of 8085 this memory happens to be a chip which is outside the memory is a location which is in a chip outside the processor. So, to access it, so it is much slower compared to on chip access line. So, if you are having communication within the chip, so that is much faster than some communication which is off chip. So, if I know that some of the variables are needed very often in my program, so I may decide that I will put it in one of those registers B, C, D, E, H, L and use that. So, that for that particular variable I do not need to access the memory. So, that way the access will be faster. So, these registers they can provide storage internal to the CPU, and there are interrupt facilities and there is internal data bus. So, these are the major components that we have in the 8085 processor. So, we will start with the ALU. So, this ALU, it as the name suggests, arithmetic logic unit. So, this is doing the arithmetic and logic operation. So, apart from this logic operation, so it also has the accumulator which is part of every arithmetic logic operation. Though in the diagram we have shown this accumulator separately. So, for all practical purposes, so you can think that the accumulator is a part of the ALU, because ALU always gets one of the operands from the accumulator and it produces result onto the accumulator. And it also has a temporary register. So, like in this diagram you see that we have got this ALU, we have got the accumulator and the temporary register. So, they are very much integrated with the ALU. So, for all practical purposes I can say that these three units are together for and becoming an integrated part of the arithmetic logic unit. Now, internally how is it implemented? So, that is not known. So, that is not divulged by 8085 designers, but conceptually it we can say that okay, they are all part of the accumulator. Okay. So, this ALU it holds a temporary register for holding the data temporarily for during execution of the program, and this temporary register is not accessible by the programmer. So, as far as the programmer is concerned, there is no such temporary register available. So, it has got the register A, it has got the registers B, C, D, E, H, L. Now, if we look into the registers, so registers can broadly be classified into two categories. One is called general purpose register and other is called special purpose register. So, general purpose registers, so we have got the registers B, C, D, E, H and L. So, these are the general purpose registers. So, they can be used singly or as a 16-bit pairs. Like you can say that so you can sometimes so this, for example, this BC pair. So, BC pair, so you can load some value onto this B register or you can load some value onto the C register. So, you can load some values there, or you can say that I will load a value into this 16-bit pair. Okay. So, this is treated as a 16-bit register, B and C taken together considered as a 16-bit register. So, that is possible. So, for pairing, so the pairing is in terms of BC, DE and HL. So, we will see some instructions later that will show you how to access this BC, DE, HL as 16-bit pair, and out of that so pairs, this H and L, they are also used as data pointer. Now, pointer, you know, that is a very interesting data structure that is there in many programming languages. So, where we do indirect addressing. So, in case of say for example, the language like C, so I can define an integer pointer int star p and sometime later I write star p equal to 10. So, whatever be the location at which p is pointing to, so that location gets the value 10. So, how this thing is going to happen internally? So, for these pointers to be supported or this indirect addressing to be supported, the underlying processor must support this indirect addressing. So, in case of 8085, so this is done by this H and L pair. So, there are instructions by which you can tell that I want to store the value 10 at the location pointed to by the HL pair. Okay. So, all memory addresses are 16-bit. So, this HL pair is a 16-bit value. So, if you say that way, so this memory location which is pointed to by HL pair will be getting the value 10. So, that actually, so if if the address of P, address of this location is loaded onto the HL pair, and after that I do this M HL gets 10. So, essentially it implements the pointer as a pointer operation. So, this H and L pair can be used as data pointer for holding the memory address. Now, apart from that, there are some special purpose registers, accumulator, that we have already said. So, this is the source and destination of all arithmetic logic operation. Then we have got some this store the result and also stores the result of these registers. So, there are some flag registers. There are some flag registers which will tell you like some status of the last operation. So, we have got this flag register which is also an 8-bit register, and it shows the status of the microprocessor before or after an operation. So, out of these 8 bits, all bits are not used, but the bits that are used are the sign, 0, auxiliary carry, parity, and this carry. So, this is the so if you look into this register, so then this bit D7, this bit D7 is the sign. So, if you do the last operation and after doing the operation, the result becomes negative. For example, suppose I have got an instruction subtract B. So, the essentially it will do A gets A minus B, and after doing the operation, if the value of A becomes negative, then the sign flag will be set to 1, otherwise the sign flag is 0. Then the next bit, bit number D6 corresponds to the 0 flag. Like if you do this operation, if it happens that A and B they were same, the values were same, then after this A will become equal to 0, and whenever A becomes equal to 0, this 0 flag is set to 1. So, many a times we need to compare between some 2 or more operands, and depending upon the comparison result we want to take some action. So, this sign and 0 flag, so they will help that way. Bit number D5 is not used, bit number D4 is for auxiliary carry. So, auxiliary carry is like this. So, if you are doing some addition, suppose this is the first 8 bit this is the A register and this is the B register. Okay, this is the B register. So, this is bit number 0 to 3 and 4 to 7. Now, if the instruction is say add, and when doing this operation, if some carry was generated, when I have added say these bit 3s, if some carry is generated and this carry is going to the next one. So, if this carry is generated, so this is known as auxiliary carry. So, it is at the middle. Okay. This is sometimes useful in this your BCD addition and all. So, you will see that. So, this is the auxiliary carry bit. Then this parity bit. So, we have already seen that whether you want even parity or odd parity. So, based on that this bit may be set to 0 or 1 to make it either even or odd. And this bit number 0 is the carry bit. So, carry is after doing this whole addition, if some carry is generated at this position. So, after you have done this whole addition, if some carry is generated, then that carry is stored in the carry flag. So, this way this flag register it uses different bits to represent the status of the last operation, and based on the value that we have. So, we can write program that will exploit the values and accordingly take some conditional decisions within the program to continue with some part of the program or to go to some other part of the program.